Okay, it's a presenter mode or, okay. So I'm going to talk a little bit about the motivation, then I'm going to go through neural network and data, and then at the end I'm going to present the results on parameterizing precipitation. So here the plot that I'm showing compares, just give me a second, sorry. Yeah, compares precipitation from observation, that's this solid line, with one climate model, that's this dashed line. And we have frequency of occurrence on the y-axis and the rain rate on the x-axis. So what we observe here is that the dashed line, like the model precipitation, tend toward drizzle. So the model predicts a large amount of small rain and then underestimate the strong rain. So to give a more accurate number, the rain event less than 1.5 millimeter per hour, or as much as like 5 times more frequent, and then precipitations larger than 2 millimeter per hour is underestimated by as much as an order of magnitude. Now, these numbers are specific to this model, but this issue exists in many other climate models. Okay, so then climate models, usually they rain too often and too little, and they have a bias toward light rain, and they have a very smaller variance compared to what we observe in real world. So it's somehow like it's very deterministic, and then the more recent approach is to add some stochasticity in order to increase the variance in predicted precipitation. Now, all these problems can be rooted in the way that precipitation is modeled. So we know that in climate models, we do not resolve any scale smaller than the grid size of the model or the time and step of the model. So that's like 100 kilometers or 15 minutes for GCM. And then the model has to rely on parameterization for the processes that are not resolved. And then the parameterization, then we can define it as a representation of physical processes that are not resolved by the model. And the assumption is that these unresolved processes can be approximated using the resolved variables. So what I'm showing here is 2 examples for the parameterization of precipitation on the left. So this is from Betts and Muller, one of the first parameterization of precipitation, that they model P precipitation as a function of W. So W is the total amount of moisture in a column of the atmosphere. So they predict it as a linear function of W, and then WC, which itself is a critical value of W depending only on temperature. So they assume that if the column of atmosphere get moister than its threshold, that moisture is going to collapse to form rain. And this H is simply a Heaviside function. And then the one on the right is a more popular one that predicts cloud condensate. So at each grid size, the model has a prognostic equation for total specific humidity. That's my QT here. And then the model also implements a prognostic or sometimes a diagnostic equation for standard deviation of that specific humidity. And then it's assigned a PDF. So that could be like a Gaussian or sometimes a beta distribution to specific humidity, and part of this distribution that has a value larger than the saturated specific humidity is assumed to condensate and form clouds. Now, these parameterization, they do not represent any information about subgrid scale structure. So it doesn't matter like if I have clouds that are staying very close or if I have a very randomly distributed cloud structure. While from observation, we see that cloud can get many different forms. Some of them, they appear very frequent that they have been given a specific names. So like flower, fish. So these are the cases for shallow clouds. But we also know that we can have different degrees of organization or many different cloud structure for deep convection, and that is way more important for precipitation because a large part of precipitation comes from deep convective precipitation. Now, my GCM does not represent this subgrid scale structure because it takes only the mean value to predict or to approximate the unresolved processes. While from cloud resolving simulation, we know that this structure is important. So from cloud resolving simulation, we know that convection can be randomly distributed That's the one on the top. So these are the same 3D outputs of the simulation. The gray color shows the clouds. And then the color on the, like the shading on the surface shows the near surface temperature. So the one on the top is randomly distributed convection. That's one of the situation in idealized simulation. But convection can also clump together and form this very strong structure that is very moist, and precipitation is happening now only in this small region, and the rest of the domain is very dry. And this can have a large impact on the atmospheric profile. For example, relative humidity I'm showing here. These are average over these two domains. We see that the case that is very organized has a very smaller average relative humidity compared to the very random case. So based on our Betz-Miller prediction, then the one on the top has to have a larger precipitation, and the one on the bottom is probably not precipitating at all based on their threshold, based on their simple model. But we know that it's the opposite. The one on the bottom has a larger amount of precipitation. So we know that organization is important for precipitation. In one point because it changes the rain evaporation. So now in the case on the bottom, precipitation is happening only in this moist region. That means that when precipitation travels through a column of atmosphere, it evaporates less because the atmosphere is more humid, and that increases the precipitation efficiency. And that means that the rain rate at the surface is larger, becomes larger when we have organization. We could also have inner cloud interaction. So that's caused by couples. When we have two clouds, the downdraft that reaches the surface start propagating out. And then if they collide, and they're going to trigger deep convection. And it's been shown that deep convection that formed because of couple interaction is more likely to develop to extreme precipitation. And then we also know that this structure can survive over time, and that means that the accumulated precipitation is larger when we have organization. Now, if we are in a GCM, we are somewhere between these two cases. Like organization can have any degree from strongly organized to very randomly distributed. While the parameterization of convection, they usually assume an ensemble of randomly distributed convection, so they do not include any interaction between clouds. We also know that organization can matter for outgoing long-wave radiation, because if we get organization, the atmosphere is overall drier, and that lets more outgoing long-wave radiation, and that can affect climate sensitivity. But in our GCM, we didn't have any interaction or any degree of organization. And we also saw that we have some shortcomings in predicting precipitation. So what we want to know here is to investigate if we need to include some information about subgrid scale structure in parameterizing precipitation, and if maybe that is the information that is missing in our parameterization. So before getting to the methodology, I want to also show those plots from Nidin that they look at precipitation from observation. So what they do, they condition precipitation on column water vapor and free tropospheric temperature. So they bin the column water vapor and they average precipitation over bins. And they show that mean precipitation has a simple power law dependency on column water vapor. And it increases at a threshold, it increases rapidly. So now we want to use this as a benchmark to evaluate our prediction of precipitation. But before that, I wanted to see if the data that I'm using can reproduce this critical behavior. So this dashed line is then supposed to have similar behavior as the one on the left. It sort of has the same tendency. So we have this strong increase, although the data is pretty much different. So this diamond data that I'm going to talk about in a few slides, it simulates only 40 days. So it has a very short period, while the one on the left is data from 18 years. So the feature space on the left is very larger. So beside this critical behavior, we also see like a strong spread in precipitation. For a given column water vapor and free tropospheric temperature, precipitation can be everywhere, like anywhere. So we want to also see if this spread is only due to stochasticity, or if we can somehow inform our model and predict part of this spread. Any question? Okay. So I'm going to continue then. So then we have two objectives. We want to see how much we can predict precipitation using only result variable. Could we reproduce this overall behavior of precipitation that we saw, the critical behavior versus precipitable water, and then how much of the spread that we see we can predict. And then the second part, we want to see if including subgrid scale structure can improve the prediction. Okay, so for the first question, I'm going to use a simple neural network. It's a fully connected feed-forward neural network that takes larger scale variables as input and predict precipitation. And the loss function is a mean square error. I'm going to talk about larger scale variable in a few slides, but so here is my parameterization again. And now what I'm going to do, I'm going to replace this F with my neural network. The data that I'm using are from Diamond simulations. So these are global storm resolving simulations that have been run for like 40 days. And the resolution of the original data is 4 kilometers, and the time step of the outputs, the 2D outputs that we use is 15 minutes. From these data, I'm gonna ignore first 10 days as they're considered as the spin up of the model. And then from the 30 days that remains, I'm gonna randomly select 10 days. And we're going to concentrate only on the tropical ocean. And then to produce the data, we're going to just coarse grain to GCM size grids and pass that as the input. So the size of my input now is only 4 dimension. I have column water vapor, that's my PW, surface temperature, and a specific humidity at 2 meters. So there's 2 meter variables. I use them to inform the model about the boundary layer structure. Okay, so the result for the baseline, if I pass as input only column water vapor and specific surface temperature, this is my result. So what I'm showing is precipitation on y-axis and column water vapor in x-axis. So the dashed line is the true value, and the solid line is the predicted one. So I'm binning again the column water vapor, and I'm showing the spread or the precipitation average over that spin of column water vapor. And then this shading is showing the spread. So we see that the model captures this critical behavior to some extent, but it doesn't capture the spread in the data. If I include 2 other variables as the input, the model better now predict the critical behavior, and it also captures a little bit of a spread. But its R square is still low. So the overall R square is about 0.45. And then the R square computed for each bin of PW is about, and the maximum is about 0.5. And if we look at the distribution, the probability distribution of these 2 predictions, so in the green is the one on the left, the orange is in the one on the middle, and then the blue is my true data. We see that the model overpredicts the precipitation with a small intensity, and then underestimate or does not predict at all the extreme precipitation. Okay, so we know now the answer to first question. We can reproduce the critical behavior of precipitation, but we cannot predict the spread in precipitation. So now we want to go to the second part. Is there any question?
Yeah, a question on how you're dealing with time. You may have explained this, I just missed it, but each day, the time step you're working on is daily?
It's 15 minutes time.
15 minutes.
Yeah.
Okay, so then how are you incorporating the lag time or the history of known?
No, I haven't included anything about history yet, but okay. I'm going to get to that. That's the last part. Yeah.
Thank you.
Okay, so then we want to include information about subgrid scaling structure. So to do that, we have to quantify the subgrid scaling structure or organization. Over the last couple of decades, let's say there has been more than 25 metrics that has been developed to measure the degree of organization, that they look at different aspects of organization. Like some of them, they look at the statistical properties, for example, the variance of precipitable water, or they might look at the some of the, let's say, cloud size or cloud distribution. or they might look at the scale decomposition. So what we did, we took these 25 metrics and we applied them to our data, and then we make a time series, and then we compute the correlation between these time series. So the idea was to somehow find out which of these metrics we can use to inform our neural network about subunit scale structure. But the pattern doesn't give a result or a hint of which of them we can use. It's pretty much a spread. But then there's also two other issues with these metrics. The one is that they're designed for large domains. So the domain, like by large domain, I mean a domain of like 500 in 500 kilometers square. So if I apply them to a GCM size domain, they may not capture any relevant information. And then the second issue is that they target a specific aspect of organization, while when I want to predict precipitation, we don't really know which aspect of organization might be important. So then to overcome this issue, we thought that we can implicitly learn organization using an autoencoder. So an autoencoder is, let's say, a nonlinear dimensionality reduction technique that has two networks, an encoder that takes a high resolution field and maps it to a very low dimension representation that we call a latent representation. And then the decoder takes that low representation and maps it back to high dimension space. Now, we don't know what this org captures, this ZL, sorry, but we know that it has to capture enough information that can be used to reconstruct the original field. So what I'm doing here, I'm passing high resolution column of water vapor as input, and I compress it to a dimension of 2 power 2. So I'm going from 2 power 10 to 2 power 2. And I want to use this ZL as to inform my network about organization. So here is then the structure of my new network, what we call org-NN. It has two blocks. On the right, I have my simple feed-forward neural network that I had before. Its inputs are larger scale variables, but I add also org that I extract from my autoencoder. So this org then goes as input to my simple feed-forward network. It gives some information about precipitation, and then it gets feedback from it gets feedback through back propagation and then goes back to encoder. So that means that my org is forced now to get relevant information related to precipitation. And I train these two blocks together. So the loss that I have now is the mean square error of this reconstruction that I have here, the mean square error of precipitation, and we add a third term that is the rotation invariant. So basically, we know that if we have an organization metric, it shouldn't be sensitive to the orientation of this image, right? So we add this constraint. We rotate any input that we have randomly, so it should be only 90 degrees. And then we pass both of them through the encoder, and we force the org of those two to be close. So we add that to our loss function. So some results, these are again from the baseline, and these are from my org-NN, and we see that now the model captured the right spread that we have in the data. So if you look at this green line, it's almost 0.8 for all bins of column water vapor. And then if you look at the probability distribution, the model captures this tail of precipitation, like precipitation extreme that was the challenge for our simple baseline model. Then we can also look at the R square computed for time series of each grid. So now for each latitude, longitude, I have several time steps, and I compute R square for predicted and true precipitation, and this is then the result. We see that it does a good job almost everywhere over the tropic. And then this result is robust to the choice of resolution, and then the dimension of work. So we tried the dimension 4 and 2, and we see that it does a good job even with only 2 org variables. Any question? Okay, so now if we know that if we have org, we can improve the prediction of precipitation, but we also know that in a GCM, we don't have access to high resolution fields. So then how we can predict our org? One solution is that maybe we can predict org from resolved variables using a neural network. So I take a neural network and I pass my predictors, my largest scale variable as input, and I try to predict my org. So what I'm showing here in org by org T, I mean the org that I extracted from encoder, and org P is the one that I'm predicting using largest scale variable. So what we see is that it's not that much predictable. So except for org1 that has an R square of 0.3, the rest of them has an R square of 0.1 that is very small. But this is not surprising because if we could learn org from larger scale variables, we didn't need to go through encoder. We could have a better prediction even from our baseline model. But this is a bad news because that means that I cannot have access to my org, but we can maybe improve that. So what we do now, we want to see if we can use the historical information from larger scale, like let's say larger scales of previous time steps, to predict org of this time. That means that we are assuming that maybe part of this structure persists over time and has a signature on larger scale, so that including larger scale of previous time step maybe can improve its prediction. So here I'm including larger scales from current time and 4 previous time steps, like 1 hour of memory. It does improve the prediction, but not that much. Like for first org, I have now R square of 0.4. For the rest of them is R square of 0.2. One other thing that we can do is to include org history as well. So we know that if we have a structure at this time, it's not totally different from what I would have 15 minutes later or 15 minutes before. So that means that we can use org history as well to predict org of current time steps. So that's what I'm going to do now. So now I'm including previous time step of org and 2 of previous time step of larger scale. And that significantly increased the prediction of my org variables. So all of my R square now are larger than 0.95. So that means that my org is actually capturing some information about subgrid scale structure that cannot be captured from larger scale, but they persist over time. So there is a correlation, a temporal correlation between the org variables that I have. So we did a little bit more of investigation on the how many time steps we need to include. So this is like what I'm showing here is R square for different tests that we did. So N of LS means how many previous larger scale time step I'm including, and N of org means how many previous org time steps I'm including. So when I include org of, previous time step of org, I always have a very high R square. But the very interesting case is the purple one, that I include only 1 previous time step of org, but no information from larger scale. And we see that R square is larger than 0.95. That means that we can use a simple autoregressive model to predict org of time t based on org of time t minus delta t. And that has a lot of advantages for implementing in GCM, because then we don't need to carry around a lot of data. Any question?
I have a quick question, and maybe you're going to get to this later, but did you look at the latent space of org at all to see like what's being represented specifically?
Yeah, so that's the next part.
Okay.
Any other question? Okay, so I'm going to pass it to Kara for the part on what org learns. Thanks so much.
I will hopefully do the same thing. Okay, can you guys see that? Or do you see my notes? Okay.
Great title.
Okay, yes, so that is the part I'm going to talk about is what does org mean? So the basic idea is that we're going to use the trained decoder to map out the latent representation. But we need to know kind of what to put in for like org to be able to do this. So first we need to know how org is distributed across the set of observations in the diamond simulations. And so that's something that I'm going to get from the encoder and just like feeding it in like the 10 days of simulations to get these distributions of org1. So I guess I'm just going to start with talking about a latent space of just 2 for the org, and then I'll get to the 4-dimensional case in a second. So this is for this 2D latent space. And so you can see that the distribution of org1 and org2, so this is the joint distribution, and then on top you see the distribution for each of the parameters. So like they're pretty highly correlated with one another, and they're also not particularly Gaussian. They have some pretty long tails. So in order to kind of take care of the fact that they are not Gaussian, I'm going to sample deciles from those distributions and then feed those values back into the decoder. And so that gives us this kind of mapping across org1 and org2. And so from this, you can kind of see that probably up here, things are more organized and like more aggregated. And then down here, things seem to be less aggregated, more just like randomly distributed, but it's sort of hard to interpret like what exactly is happening along the diagonal and like how exactly this is, how exactly to interpret this. So one thing that I've just tried actually is to apply a principal component analysis to org1 and org2. And then here I'm plotting the distributions of the first 2 principal components of the latent variables. So now you can see, at least for org2, it's much more Gaussian. Org1 still has like kind of a long tail. But now if I basically, and I could look at also the explained variance ratio. So actually the majority of the variance is explained by like the org1, what I'm calling org1 prime. So that is the first principal component from the PCA analysis. And I can do the same thing of mapping out the deciles of the distributions now for org1 prime and org2 prime. And so I think in this case, it's much clearer to see that as you go towards the right for org1 prime, it's much more aggregated and significantly less aggregated like on the other side. And then it's a little bit less clear exactly what org2 prime is, but as I've said, it's like the majority of the variance is actually explained by org1 prime. Oh, and then I should say for this, I'm scaling this relative. So each box is, or like each high resolution field is like scaled relative to the maximum value in the field. But I can also look at the absolute scaling to like, so now it's scaled relative to the maximum value in the data set. So this suggests that it's not just learning something about the column water vapor, but it's actually something about organization or the aggregation, the subgrid scale aggregation. So I'm now going to do the same thing for the 4-dimensional case. And again, if you just take the values directly learned by the encoder, they're actually, again, very highly correlated with one another. So again, I do like a principal component analysis and find again that the first principal component actually explains like the majority of the variance in our data set. And so I'm again going to do the same thing now for org1 prime and org2 prime for the 4-dimensional case. And you can see it like looks quite similar to what was learned for the 2-dimensional case. And like to convince you of that, I'm putting them side by side. So this is what we learned for the first 2 principal components for the 4-dimensional latent space. And then this is the same for the 2-dimensional latent space. So it seems, so it's, it's not exactly the same if you look at the details, but like the main variance being explained by this like increasing aggregation seems to hold true for both cases, and that's the parameter we're learning. So you can also look at some of the other modes of variability that we learned for the other like org1 prime and org3, org4 prime and org1, but I think it's a little, I find these a little harder to interpret, but at least we see some differences in like terms of like what the fields look like. So yeah, I guess maybe the conclusions I think from this are that the greatest variability in the org parameter seems to be related to how aggregated that subgrid scale PW field is, and this is very consistent between across different sizes of latent spaces. And this basically implies that we might only need just a single parameter to parameterize that subgrid scale organization, because that's explaining the majority of the variability. Cool. That's all I had. Did you have more, Sarah?
That's all from my side. So if any question.
Can I ask a question?
Sure.
I'm curious if you looked at how the latent space like metric of organization correlates with other more well-established metrics of organization.
I started to do that, but one of the challenges is that, like as Sarah said, a lot of the organization parameters are actually designed for much larger fields, so they like don't give values that are very they don't necessarily give values that are very interesting. But I think that is like something that could be explored in more detail, and like should probably be explored in more detail. But
I also did a test related to that. So I replaced the org that we learned with simply the standard deviation of 2D field. And the result was that like it improves the prediction. Let's say if my R square without any org is 0.5, including standard deviation would increase it to 0.6. But it wouldn't improve that much the prediction of extremes.
I have a quick question. Do you plan to, or have you think of strategy about how to incorporate this to the current GCM parameterizations?
Yeah, so one thing that is nice is that we find that we can use an autoregressive model to predict org. So that means that it's not that complicated to implement it in a GCM. We only need to, let's say, sample from our latent space to have the first org of like, let's say, first time step, and then we can go forward using our autoregressive model to predict the future org. But for implementing in a GCM, we need to train probably our network on the whole globe. So for the moment, it's only tropical ocean. We don't have land and we don't have the extra tropics. So probably that would be the next step if you want to go forward with implementation.
Thank you.
But if I may, I think one thing I find really cool here is that it means that potentially you don't need a stochastic parameterization. So that's a huge thing, I feel, because I mean, you never know how to actually parameterize them anyways, you know, it's very empirical. So, and you don't know how to advect that in space and time. So I think it's very clear metric, you know, if that can be implemented, of course, you know, but that would be great in that case.
Is that why you chose to use an autoencoder instead of a variational autoencoder to try to stay away from stochasticity?
Not really. So I didn't want to use a variational autoencoder because I didn't want to impose the distribution of the org variables. Yeah, that was the main reason. Although we talked about trying if we can find out the if a variational autoencoder works as well. But then it's interesting because if we don't impose the rotation invariant, the org variables are sort of like very independent. So they are, let's say, I don't have the generative part of my variational autoencoder, but I have the disentanglement between the org variables.
May I add to that? Sorry, Sarah. So Sandra, there was also the point that early on, you know, the target was actually a probabilistic loss, like a stochastic loss. So targeting the mean of precipitation and the variance together, because the hope was to try and learn the stochastic parameterization. So as a mean and a variance, let's say. So you could think you're targeting not just a mean value with a neural net, but you're targeting basically a parameterized distribution. But then in the end, it seems that the organization, it just happens to be that the organization explains all of the variance pretty much. So there's really no need to that. So in the end, in fact, in the revised paper, like that got removed, so now the target is just a regular mean squared error. So basically you don't need even like the stochasticity altogether, which is kind of interesting. So there was more complexity before and less. Sometimes it's nice when you have less complexity.
I was going to say also, like, just I found like that training a VAE is significantly more challenging than training an autoencoder. Like, because you have those two different loss terms that are trading off, and there's like, these different methods to deal with that, like sort of cyclical annealing and things like that. But I personally haven't had like a lot of success with that for some of the problems that I've tried applying like VAEs to versus like autoencoders. But
And the other question, this is actually kind of, so there was a talk in the AI2ES kind of seminar series yesterday about from Ashish Chattopadhyay on some of the, which y'all may be aware of, on some of the work he's doing with kind of forward prediction of like, I guess, the digital twin type models. And one of the things he was discussing pretty heavily is this issue of spectral bias, where the model predicts the large, basically this large wave number, or sorry, large scale modes, but puts too much energy in the small scale, and thus the model blows up if you integrate it forward. I'm wondering how much of a connection there is between some of the stuff he's seeing with that, and his solution was to do like basically a spectral regularizer to force the model to try to recover these small modes. I wonder if what kind of connections there might be between some like this kind of approach and the trying to model the organization, which is again like a smaller scale features, and kind of trying to organize them and force the model to actually account for them more explicitly.